In terms of the preceding video, look at the expressions we obtained for the case where we break the interval from A to B into 4 subintervals. How much of what's here actually depends on the fact that there are 4 subintervals? Well, the only thing that really is related to the 4 is the 4 here and the 4 here. Everything else could apply if we had 100 intervals, or 10,000 intervals, or 28 billion intervals. We wouldn't want to actually do the calculations for 28 billion intervals. That would take a while. But the only thing, again, that depends on the fact that we have 4 intervals is the number 4 here. What if we had 6 intervals? Well, where did the 4 come from? We divided the length of this interval by 4 to get the length of each of the subintervals. If we had 6, we would be dividing by 6. And that would give us a 6 here and a 6 here. If we had 28 billion, well, we divide this distance by 28 billion to get the width of each of the very slim intervals that you would end up with. And then we'd have 28 billion here, and we'd have 28 billion here. So what if we just let n stand for the number of intervals into which, subintervals into which we're going to divide our original interval? What would we have? Well, in order to get the width of one of the n equal subintervals, we would have to divide this distance b minus a by n, which means that that 4 would become an n, that 4 would become an n, and that 4 would become an n. So now we have, we're going to be able to write down the entire scheme. Okay, and that scheme would then be very easy to program, for example, on a computer. But it also is very handy in representing exactly what we mean by each of these calculations. So we're going to do that. Now, instead of a nice continuous graph, we want to represent a graph where we could have any number of intervals. So it means we're going to have to break our x-axis and we're going to break our graph. So we only show the first couple of subintervals over here and the last couple of subintervals over here, and there could be any number of intervals in between. So this distance that we represent by this break and the graph that we represent by this break could be quite extensive. It could go for thousands of miles. Okay, so we're going to calculate our interval width, and using that we're going to label x naught is going to be A, x sub n is going to be B. Now this is going to be, we're going to use n subintervals. So use n subintervals from A to B. And I maybe should have said n equal subintervals. That could be implicit, but I'll write that out explicitly. Okay, so if we know A and B and we know n, then we easily calculate the width of an interval, and each interval is of width total distance from A to B divided by the number of intervals. So it's going to be B minus A over n. Then we can label our projection lines. I'm going to draw those and label them off camera, just in the interest of your time. Okay, I've labeled all these intervals. And I've not only labeled y naught, y1, y2, yn minus 2, etc. I've labeled and indicated the slope segments, or the approximating segments, m1, m2, m sub n minus 1, m sub n. Obviously there are n intervals, so this last one has to be m sub n. The one before that's m sub n minus 1. Just as the last y value is y sub n corresponding to x sub n. This one here is y sub n minus 1. It's kind of a blue looking n there, but that's what it is, corresponding to the n sub 1 subscript on the x value here in the coordinate, and y sub n minus 2 corresponding to x sub n minus 2. And once more, the values of y presumably can be calculated once we've figured out the values of x, and the values of x are easily calculated if we know the values of a, b, and the number of subintervals. And we've similarly labeled the areas A1, A2, A sub n minus 1, A sub n, and accumulated areas AA sub 1, AA sub 2, AA sub n minus 1, maybe a little hard to read, and AA sub n. So now I want to label the typical trapezoid, the ith trapezoid. Don't know exactly what it'll look like, but here's a representation of it. It's going to be a trapezoid. And it's going to have graph altitudes y sub I minus 1 and y sub I, since the ith trapezoid has right-hand altitude y sub I. Now, what's the width of the trapezoid? Well, the width of the trapezoid is the same as the width of every trapezoid, b minus a over n. So I'm going to label the width b minus a over n. Now, in terms of this, this, and this, I can write out the expression for m sub I, the expression for a sub I. And, of course, we can include the calculation scheme for the accumulated areas. Okay, before you look at what I've written, you ought to think about what these expressions would be, but here they are. Mi is just rise, which is yi minus 1, divided by width, which is b minus a over n, and we can simplify the complex fraction by putting n here. We get yi minus 1, divided by the quantity b minus a. I got a little bit crowded there, but that's a very straightforward rearrangement. And a sub I then is what? The average of the two altitudes. Add these, divide by 2, multiplied by the width, b minus a over n, nothing to it. Accumulated area of the ith trapezoid is the accumulated area through the ith minus 1 trapezoid plus the area of the ith trapezoid. That gives us the accumulated area through, excuse me, the ith trapezoid if I is greater than 1. And if I is equal to 1, well, we have accumulated area 1 equals the area of the first trapezoid. So what we have here is simply a calculation scheme that can be applied. If we have the information, if we know A, B, and the number of intervals we want to divide into, and if we have a way of evaluating the function for every value of x, then we can follow this scheme and we get all this information. Now let's see what good this information might be.